Okay, we're going to start on Chapter 2, 2.1, Relations and Functions. We'll do 2.1 as a short lesson, and so is 2.2, so we'll do them both today. You should have a note packet for these slides with Chapter 2.1, Relations and Functions on it. Start off with a little bit of a review, and we can solve these, so go ahead and solve these. 2c minus 10 minus 2 is 8. 2c minus 12 is 8. 2c is 20. c is 10. Very nice. Very nice. Graph the solution set on a number line. I'm going to take this. We're going to solve. Add 5. Watch your signs. Going to have, after we add 5, we have 4. Divide by 2, and I get b is less than 2. Remember, less than or equal to. Remember, if it's positive 2, we got a closed circle, shade to the left. Little review from last chapter. Same thing here. Write words into symbols. 4 plus a number divided by 6 is equal to the product of 12 and the same number. Now it just said 4 plus, so we just want to go 4 plus that number divided by 6. If they had us say the sum of number and 4 first, then we would have to divide everything by 6, is equal to the product of 12 and the same number. Slope on the bottom, y2 minus y1 over x2 minus x1 gives me negative 7 over negative 6. Which is 7/6. I'll review from what we've done in the past, hopefully not too difficult for you. Okay, so we're going to talk about a function today. So we go to the store, and I got a list of things to buy from the store, and I'm going to buy some peanut butter. I'm going to take this Jif peanut butter. Gavin likes peanut butter. So we're going to go, and that's going to cost me $4. And then I'm thirsty, so I'm going to have some Mountain Dew. Drink Mountain Dew and you'll discover whatever. And it's only $1. I bought a little one, $1. And then I'm going to buy a can of pork and beans. I don't know how many of you have bought pork and beans in the past, but it's not very expensive, and they're on sale today, and it's also $1. And then I need to pick up some Rogaine because, you know, times are tough, and we go, and it costs $22. So when we're talking about a function, we're talking about our input values and output values, and basically it comes down to that if you're going to go to the store, say you went to the Coburns and you bought this peanut butter, there's only going to be one price for the peanut butter. There's only going to be one price for this particular Mountain Dew. There's only one price for the pork and beans, and there's only one price for the Rogaine. Okay? And what it makes it a function is that you can't buy the same item for two different prices in the same store, obviously. So when we're talking about a function, we're talking about each one of these inputs, when I input it, can only have one value assigned to it. Now, notice over here, we got lots of stuff that's $1. If you think about going to the dollar store, everything's $1, but we would have each individual item can't have more than one price coming out of it, so we're good to go. Let's take a look at a few more examples. The function is a relation, which is a correspondent. Now, a relation, it's not a relation, it's not like a relation between a boy and a girl. Relation, it's just a set of ordered pairs. That's all it is. Set of ordered pairs. That's important. Ordered pairs. And then we determine whether or not it's a function. And it says each element of x is matched with one and only one y. That's what we saw on the previous screen, where peanut butter can only have one price. Peanut butter was the x values, and the price was the y values. The set x is called the domain. So whenever they ask you about the domain, that's the set of all x's, all of the inputs. And then the y values are called the range. Range are also known as the output. So all of these are interchangeable terms. In terms of x and y, Each x value can only have one y value, and that's going to be the biggie. The x values can only be partnered with one y value. You can't have the same x going to two different y values. You can, as we saw with the Mountain Dew and the pork and beans, you can have the same y value for each individual x. So the function of peanut butter was the input, and I think the peanut butter cost us $4. And then like the beans, they cost us $1. So this would be function notation. F of peanut butter, the cost of peanut butter is $4. Input, output, input, output. Next, these would be relations. They're just relations right now, set of ordered pairs, and it says list the domain and the range. So the domain here, when we're talking about a set, we're talking about chicken lips. So I say I've got and I can just list them 3, 4, 2, and 5. Those are the x values. These are going to be the domain. These are going to be the range. So the range here, I got 5, 7, 2. Some people might want to put them in order because, you know, OCD, but you don't have to. And then you ask yourself, is this a function? And you're just looking at the domain. A 3, a 4, a 2, and a 5. I said them all once. It doesn't matter that the 5 is double up in the range. So this is, yes, it's a function. All of the x values have only have only one y value. Over here, domain, again, all relations have this. If I wanted to say I got a -1 and I got a 2 and I got a 2 and I got a 4, red flag. We've got a couple of 2's there, but first let's list the range. -1, 2, 3, 6. And the answer for is this a function? We're going to say not a function because 2 is paired with -1 and 2 is paired with 6. How could, this is like the same peanut butter, how could we get two different prices for the same peanut butter? We can't. Okay, so you're basically looking at, does any of the x values double up? Do any of the x values double up? Over here it's yes, over here it's no. That makes this a function, and this is not a function. Domain is set of all x's, and the range is the set of all y's. Okay, this is a mapping. Very easy to see on a mapping whether or not you're a function. Again, domain and range is going to be just the set of all x's and the set of all y's. Domain, I got my 0 and my -5 and my 11 and my 14, no big deal. Now the range values here, I got 0 and -5 and -2 and 3. Not all of them are being used, but they all are a part of the range. So this is the domain, this is the range. This is the domain, this is the range. And this one, again, I'm 0, one partner, -5, one partner, 11, one partner, 14, one partner. So yes, that's a function. Over here, I've got 12 is an issue. 12 is paired up with two different values, so this is a no. I do write the domain, -2, -5, 12, and 14. They're all there, okay? And then I've got 0, -5, -27, and 3. So the issue is the double coming out of here. These ones are all okay because there's only one line coming away from each of them. I think that's the easiest place to see whether or not something is a function. Then we can graph. This is going to be you could graph this on your calculator and get a table of values, or maybe you know that this is a parabola that is going to be 1 unit up, so it's going to look like this. Take my word for it. Okay. Whoops, now I got to try to draw a straight line. Good luck. Okay, so there's my parabola. And then if we're talking about the domain, talking about x values, notice you can put anything in here and square it. So the domain is going to be everything. In interval notation, I would say my domain goes from -infinity all the way to +infinity. And that's because this is x values could go, this arrow is going to go all the way to the left and all the way to the right. Now my range is going to be a little different. How low do we go? My lowest y value, again, these are domains, the x values, and I can be anything. Range is the y values. Well, what are you going to get out? Your lowest value is +1. So I can be +1. I don't go any lower than it, though. And then I go all the way to infinity, because this is the low value and it goes up forever. Okay, and it can go all the way to the left and all the way to the right. Input values, x's can be anything. Range values, I'm going from 1 included, that's why we have a bracket and interval notation, goes forever. Graph this guy, I got a y-intercept of 5 and then a slope of positive 2. So I graph my line and I connect the dots, la la la, and it goes on forever in both directions. So if you think about the x values, anything we can't put in here, nope. We can go from negative infinity to infinity, both with what you know about linear functions, as well as this is going to continue going down into the left and up into the right, which brings us to range. It's going to be everything, all real numbers, negative infinity to infinity. Same thing here, state the domain and the range. Now we're just on the graph. So again, domain, x values, I would just start myself on the left-hand side, -4, -3, 0, 1, and 3. Those are just the x values, right, the domain. Here's my x values for each of these guys. And then my range, I can go with, I'm going to go from bottom up again, -2, +1, +2, +3. Notice there's 2 -2's. We don't care about that though. It only matters whether or not the x's were matched up. So we can take a look here. There's 1 x value on each line. So this is going to be a yes it is, because all of the x's only have a single y output. Which leads us directly to the vertical line test. As we run a vertical line from left to right, it's very important. Whoa, 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 whoa. Okay, let's try that again. As we run a vertical line from left to right, if you only touch the graph in one spot, that means that there's no doubled up x value, which means you're going to have a function. So this is very important that you can visually look at a graph and quickly determine whether or not it's going to be a function. This one's a yes. Any linear function, y equals mx plus b would work. And then now, if you look at this guy over here, as I run a vertical line through, I hit one spot at that vertex there, but then I hit 2. As soon as you fail and hit 2 one time, it's a big fat no, not a function. Okay, so anytime you got 2 of them going through there, it's going to be a no. So think about running a vertical line through from left to right, because vertical lines are going to be the x values. So as I run a vertical line through here, I'm going to hit in one spot, one spot, one spot, one spot, one spot, one spot, everywhere. That's going to be a yes. This little sine curve looking guy here, one spot, one spot, one spot, one spot, one spot, everywhere. And so that's a yes. So the graph of a sine and cosine. And then this is looks like an ellipse. And as soon as you hit 2, it's a failure, so it's no. You could hit the 2 anywhere you so choose. That means, like, if you just look right here, 0 has an output of 3 and 0 has an output of -3. How can you have the same x value have 2 different y values? Remember, peanut butter can only cost 1 price. Last thing in section 2.1 is evaluating functions. I like function notation because it lets you see the ordered pair right out front. F of -2, this is telling you what to input. I'm going to input a -2 everywhere I see an x. -2 cubed minus 3. Please watch out when you put a negative, when you have to cube it or square it. You need to make sure that you're doing the correct operation on your calculator. I like to put them in parentheses. It will lead to less errors. -2 cubed is -8. If you don't believe me, then check it on your calculator. -8 minus -3 is -11. So f of -2 is -11. So when I input a -2 for x, I output a -11. -2 is in the domain, -11 is in the range. Sometimes they give you values that have different variables in them. That's okay, don't be alarmed. It tells you to input 2t everywhere you see an x. So I put 2t in here, and I'll cube the whole thing, minus 3, which means I'll have 2 cubed is 8, t cubed minus 3, and that's it, f of 2t. So you have created a new function for f of 2t based on the original function. Same thing down here. What I really want to take a look at here is watch out for that negative sign. I'm going to put this g right in for all the x's. The negative is part of the equation. Negative 2 squared minus 4 times negative 2. And I get negative is outside the squared. Now I square the negative 2 and get 4. And this is a negative times a negative, which is plus 8. Negative 4 plus 8 is 4. So you got to watch your negative signs on these ones. If you get a little lazy with it, you're going to be in trouble. Make sure you're showing your work. So g of negative 2 equals 4. When x is negative 2, y is 4. And then fractions are not your friend, but you can handle them. And I put a half in, and I square it, minus 4 times a half. And when you square a fraction, remember, you square the top and square the bottom. So it's 1/4. And 4 times, whoa, this should have been 1/2. Almost made my first mistake of the year. And I get 4 times a half is 2, which leads me to negative 2 and 1/4. So I get g of 1/2. So an input of 1/2 is an output of negative 2 and 1/4. So we're putting in domain values and getting out range values. Discrete and continuous. Discrete is going to be countable, something you can count. I can count the number of students in this class, 1, 2, 3. And continuous is going to be a measurement. Whoa. Continuous. So this is countable. Discrete is countable, and they're going to be dots. Always going to be dots. And continuous is a measurement, and they're always going to be lines. In order to be continuous, you have to have your pencil on the paper, and it needs to never come off. It needs to never come off the paper. Even these funky ones down here, this is continuous because my pencil never comes off the paper. In order to plot these ones, I pick it up, I pick it up, I pick it up. As soon as you pick your pencil up one time, something is no longer continuous. Discrete is going to be countable in dots. Measurement is going to be continuous. In order to determine whether or not you are discrete or continuous, you want to think about whether or not something is countable or something is a measurement. This one's a bit of a trick. Table of values for miles per gallon. Obviously that's a measurement. But if you were going to graph this information based on what we know, we would go something like years on the bottom probably. 2001, 2002, 2003, 2004, and then maybe we would go up to 20 and 22 and 21. And how would we plot these points? We would put a dot on here at 20.8, and a dot at 20.6, and a dot at 20.8, and a dot at 20.9, and a dot at 21.6 and 22. And since they're dots, it's going to be discrete. So you got to be a little bit weary of don't just go with measurement. You have to think about what does the graph look like. And since it's just dots, it makes it discrete. Commuter train costs $7.25. The cost of taking the train X times can be described by this. Now, if you just glance at this, you would say, hey, that's going to be continuous because it's a line with 725, where y is the total cost. Determine if it's discrete or continuous. But let's think about the value of x. This is x times. You can take the train once, it costs you $7.25. You can take the train twice, it costs you $14.50. You can take the train 3 times, it costs you $21.75, which means you can't take the train 1.5 times. So you're going to just have plots of 0 times costs you 0, 1 time costs you 7.25, 2 times $14.50, 3 times are going to be $21.75, and so on. And since each of them is an individual dot, it's countable. You can count 1 time, 2 time, 3 time, 4 time, and you get your answer. So it's going to have to be discrete. Last thing, 2.2, linearity and symmetry. What are the first 4 letters of the word linearity? It's a line. So really all we're going to be focused on is, can something be written as a line if it's going to be linear, which means y equals mx plus b. And then symmetry is something that you talked extensively about in geometry class. So in order to be a linear function, we should be able to change it into y equals mx plus b, or f of x equals mx plus b. State whether the following is a linear function. This is going to clearly be yes. We have a slope of 2 and a y-intercept of -5. This has a cubed. A cubed has no part in a linear function. Actually, that would look like that, in case you're wondering. And then this guy down here looks like it's almost in standard form, but it is something that we could write in y equals mx plus b form, divide by 3y equals 7x plus 4. That's going to be a yes. So you're looking for, can I write something in y equals mx plus b? If you've got square roots or squareds or cubes or things, any other power like that, then it's not going to work. Line symmetry means you can cut the graph or the picture in half. This would have line symmetry going right down the middle. There's two congruent halves. I could fold it on top of itself. So this has line symmetry, and we would say at, and that would be x equals 0 or the y-axis. This has point symmetry. It can be rotated around a point. If I rotated this 180 degrees this way and 180 degrees this way, it ends up on top of itself. So we'd say point symmetry at 0, 2. Okay, so point symmetry is rotational symmetry. Line symmetry can be cut in half. Lastly, we've got line symmetry here. We've got line symmetry here. We've got line symmetry going this way. We've got point symmetry here. We've got point symmetry here. And ooh, look at this fun little bugger down here. Looks like a bat. I should tell you the story about a bat landing on my face sometime. Okay, we've got line symmetry there. We've got line symmetry there. And we've got point symmetry here. So we've actually got multiple things. And that's all she wrote. You got a worksheet for, for homework. Please get that done. Hopefully everything is wonderful. Have a great day.